Good morning everyone. Welcome to the demonstration for the detection of stator winding interturn short circuit fault in a three-phase induction motor using Wing technique. This is the complete experimental setup for performing experiment to detect interturn fault in the induction motor. This is a three-phase wound rotor induction motor and it has the rating of 7.5 HP and 400 volts. There are R, Y, B and the neutral terminal of the motor. The motor is coupled to a DC generator. This is a three-phase thermostat used to vary the voltage gradually. It has the input terminals and output terminals R, Y, B and N. The input terminals are connected to the supply system and the output terminals of the thermostat are connected to the motor terminals. This is the main switch and the three-phase supply system L1, L2, L3 terminals and the neutral is there. This is a starter used for starting purpose. Using the external resistances connected in the rotor circuit. This is a variable rheostat to vary the severity of the fault and used for safety purpose. The box arrangement is provided to create the interturn short circuit faults on U, V and W phases of the stator winding, from where the different number of turns can be shorted. So here we can create the fault. This is a power quality analyzer to measure the voltages and currents. And also we can observe the waveforms and the phasor diagram. We are going to take the two sets of readings, one under healthy condition and second under interturn fault condition. So here we can see the scope phasor diagram. So we can set as per our requirement whether we want to see the phasor diagram or the waveform on the screen of the power quality analyzer. So now let us start the motor. And we will measure the speed using the tachometer. So main switch, we are going to switch on the supply to the motor. This is on now. And now we will vary the voltage applied to the induction motor using this three-phase thermostat. So we are gradually varying the voltage, and when the motor reaches the rated voltage, then we can vary the resistance in the rotor circuit. So here we are measuring the speed of the motor in RPM using the tachometer. We are gradually varying the voltage, and when we reach the near to the rated voltage 400 volts, we will take out the resistance, starting resistance, and will reach the running position. So now this is under running position, running condition of the motor, and the motor is operating at the no load speed. So these are the waveforms you can see. under the healthy condition. This is the no fault condition of the motor. We are watching the waveforms, phasor diagram, and the magnitude and phases of each of the voltage and current quantities. This is the observation table where we have noted down the voltages, phase voltages and phase currents under normal condition. Similarly, we will observe the waveforms under the faulty condition. So using this variable rheostat, we can create the fault. So on the V phase of the motor, the V3 and V7 terminals tappings are shorted, 11% turns are shorted, and the resistance is at maximum position for the safety purpose, and then we can vary the resistance. We can decrease the resistance to increase the severity of the fault, so that the loop current will increase and the fault severity will also increase. And then we can note down the variation in three-phase currents when the turns are shorted. We can see the change, we can see the increase in the current of the respective winding where the fault is created on the power quality analyzer. Here we are varying the resistance from maximum to its minimum value in order to increase the severity of the fault. And here we can observe the increase in the current of the respective phase where we have created the fault. So on the B means V phase, we are getting the increase in the current. Thus the unbalanced is produced in the three-phase currents due to the interturn short circuit fault. So once we have taken the readings, then we can apply the Wing technique using these currents. So initially we will apply the correction coefficient to calculate the corrected values of the currents. Then we can determine the symmetrical components of the current, positive sequence and negative sequence, and using the positive sequence and negative sequence, real and imaginary imaginary and real parts, we can plot the loci. So we get the two loci, and using this loci we can calculate the displacement angle, the travel of wing and the area of wing to predict the severity of the fault. So this way the Wing technique will help to determine the severity of the fault. This is the observation table to apply the Wing technique for stator winding interturn fault detection. The three-phase stator voltages and currents are noted down for the healthy, that is no fault condition, and the faulty conditions such as 5% and 10% turns shorted on the stator winding of a motor. As the voltages and currents are not balanced under normal operating conditions, the voltage and winding asymmetry correction coefficients are determined. Hence, voltage correction coefficient termed as alpha coefficients are calculated for each condition, and also the per phase equivalent impedances are calculated as shown in table 2. Asymmetry coefficients are calculated under the healthy condition, and they are considered to be fixed for a particular load condition. Using this alpha and beta coefficients, corrected values of three-phase currents are calculated. For the no fault condition, these currents are equal in magnitude and 120-degree phase displaced. However, for the faulty condition, they are not balanced. The symmetrical components are extracted from the three-phase stator currents, and the loci of the real and imaginary components of the positive and negative sequence components are plotted. From the loci, the coordinates are selected for Imax, and then the parameter under different conditions, that is no fault condition and faulty conditions, are calculated. Parameters has 0 value for the healthy condition, and their values increase with the increase in the severity of the fault. Thus, it helps to predict the faulty condition and the severity of the fault.